So once we have trained the LSTM network, one thing we can do is we can just directly get the performance by using some kind of matrices. But this does not give us a whole idea of what is going inside the network, what is going inside this black box network. So rather in this video, we'll try to visualize some internals of this network after we have trained it. For that, we are going to leverage the t-SNE based visualization. This is just a fancy principal component analysis. So what we are going to do, first, we are going to use our raw data. In this case, our raw data will be a W cross 52 tensor because W is our length of the sliding window and 52 is the number of features we have. We'll pass it through our t-SNE reduction, which will basically reduce the dimensionality of our input data into two dimensions so that we can easily visualize this on a two-dimensional plot. And then we are just going to put a scatter plot of this in two dimension where x-axis represents the first principal component, you can say, and y-axis is the second principal component. And the color of the classes will the color of the plot of the scatter plot will represent the corresponding class. So the better is the separation between each group of clusters or the classes, that means our network is performing better. So let's see. So that was for the data when we have not trained anything. But now we need to see inside the neural network. For that, what we are going to do? For that, let's say we have our trained neural network here. And next step, what we're going to do, we want to chop off the output layer or the classification layer. Then we are going to pass in our input feature, our input, which is W cross 52 dimension, and our output will be a single vector because it will pass through our recurrent trained neural network, and our output will be fully connected network. In this case, I am taking my fully connected network, which has 300 neurons, so my output will be 3 cross n cross 300. Next, I'm just going to put this X embedding into my t-SNE and I'm going to convert it to a two-dimensional vector. Then using a scatter plot, I can see how my class discrimination is. If my classes are well apart from each other, that means my LSTM network is able to learn very good feature and it is able to classify properly. All right. So let's see how we are going to execute this in the Jupyter notebook. So here is the Jupyter notebook. I'll provide the link to this Jupyter notebook in my GitHub and you can access this as it is. In the first step, we'll import necessary libraries. We'll do the t-SNE visualization. So for the first, what I'm going to do, I'm using my X-train data. I'm reshaping that so that it will have a flattened vector, not a tensor instead. And then I'm using that to fit for a t-SNE model with n components too. And the output will be X embedded. So X embedded is basically a two-dimension, is a list, is a array where each sample is two-dimensional. And Y label is the corresponding fault label. And then I'm doing a scatter plot. So first, before training, we can see that how our scatter plot looks for different type of fault. The color represents the corresponding fault. We can see there is a lot of mixing between different fault label. All right, and after training the LSTM network, so what we are going to do, we are going to chop up the classification layer, and we are just going to take the embeddings from the panel second last layer. For that, we are creating a new model, intermediate model, which will take our trained LSTM models input and our trained LSTM models second last layer, and the intermediate model looks something like this. The input is same, but it does not have a classification layer, rather a output dense layer with 300 neurons. And then what we are going to do, we are going to pass our trained dataset through this intermediate model to get the intermediate state of this 300 dimensional vector. Then we are going to do the same thing. We're going to feed a t-SNE model using this x inter, and then we are going to plot it with the corresponding hue. And now we can see that the corresponding fault labels are grouped very well together. This is after training of the neural network. This means our network has learned very well how to distinguish between different classes. So that is a very good case. And yeah, so that was it about this video. And in the next video, we'll see how we can use convolution neural network for the same scenario. And yeah, I hope to see you soon in the next video.